to my opportunity to ask practice problem questions on the trig substitution, and so I'm going to hold off on those until Wednesday, and we will open class with questions about trig substitution and then also improper integrals. Okay, so 6.6, improper integrals. I'm going to write down a bunch of examples here of what are called improper integrals, and here they are. We have the integral of 1 over x squared dx evaluated from 1 to infinity.
That's nice.
And we have the integral from negative infinity to positive infinity of 1 over 1 plus x squared dx. And so at this point you might be saying, oh, improper integrals must have something to do with that infinity sign. Here's another improper integral. The integral from negative 1 to 1 of 1 over x squared dx. I'm going to write down two more examples up here. The integral from 1 to infinity of 1 over x dx. And finally, the integral from 0 to 1 of 1 over the square root of x dx. These are all examples of improper integrals. Now, there's an unfortunate English language issue here. We just talked about improper fractions. And an improper fraction is a rational function where the degree of the numerator is greater than or equal to the degree of the denominator. Here we're talking about improper integrals. Now, this word improper is still used in the sense that it's something that's slightly different from the norm, but we're not talking about degrees of numerators and degrees of denominators here. So what is an improper fraction? All right, improper, the word improper in the sense of improper integral, the word improper acts as a warning that these integrals differ from our standard integral from a to b of f of x dx, where the interval from a to b is a finite interval, and f of x is continuous on that interval. So you might remember back in Calc 1 when you learned the fundamental theorem of calculus part 2, the one that said if you have a definite integral, you can evaluate that definite integral by finding the antiderivative and then plugging in the top and the bottom bounds and subtracting them. But there were some rules about that. In particular, when we talked about the bounds were regular numbers. So the interval was a finite interval, meaning you had a starting point and a stopping point. And not only that, but there was a rule about these integrals that function, the integrand here, must be continuous over the interval from a to b. And so we needed those rules, and we kind of swept them under the rug when you were first learning this fundamental theorem of calculus. And I only, and if you were in my Calc 1 class, I only gave you integrals that were continuous over that interval, so you didn't have to worry about it. But there are lots of integrals that have discontinuities and issues with them. And also, we may want to talk about having infinity as one of our boundaries. And so here's the issue. We can have, number one, the first reason that an integral might be improper is that the interval of integration might be infinite. So, for example, this first one here, the integral from 1 to infinity of 1 over x squared dx, if I draw a picture of this, here is 1 over x squared, and here is x is equal to 1, And this first integral up here, the integral of 1 over x squared dx, starting at x equals 1 and going off to infinity, says that I am looking for the area under 1 over x squared, starting at x equals 1, and adding up all the area until I hit infinity, which is really far down the way. The other possibility, the second possibility, is that our function f of x is unbounded on the interval of integration. So, for example, if I'm looking at 1 over x squared, the integral of 1 over x squared dx, starting at x equals -1 and going up to x equals +1, this function in the middle here is undefined when x is equal to 0. And in fact, when I draw a picture of this, f of x is equal to 1 over x squared, and I start at x is equal to -1, and I end at x is equal to 1, well, I'm talking about all of this area in here, but there's no top on my function here to hold that area in, and so it kind of spurts out the top like a volcano. And so here's an example of an improper integral because my function is not bounded. There's nothing that's holding that area in. Okay, are there any questions about what an improper integral is? 2 ways an integral can be improper. Okay? So let's take a look at some of these integrals. So the integral of 1 over x squared dx, starting at 1 and moving off to infinity. So I look at this integral, and this integral is improper because I've got an infinity as one of my boundaries. Okay. So I immediately say, my fundamental theorem never told me what to do if I had infinity as a boundary. It only told me how to evaluate these things if I had numbers here. So what I'm going to do is, I'm going to fix that. I'm going to look at the integral of 1 over x squared dx, starting at 1 and going up to some really big number. Now, what is that big number going to be? I don't know. I'm just going to call it b for big number. And so if I look at this integral, and the picture that I have in my head is that I have f of x is equal to 1 over x squared, starting at x is equal to 1, and stopping at x is equal to b. Now, that's not totally legitimate, right? I mean, I don't really want to stop this. I want this b to be as big as I can possibly make this. So right now, this is a very, very proper integral. Proper and correct because I now have numbers on my boundaries. But I've kind of tweaked this a little bit, so it's not exactly the same as what I had started with. I really wanted to go from 1 up to infinity. So I'd really like this big number to get as big as I possibly can. So I'd like for b to approach infinity. What kind of notation do I need for that? Limits. Yeah, I need a limit. So really, when I'm evaluating the integral from 1 to infinity of 1 over x squared dx, what I'm really looking at is the limit as b goes to infinity of the integral from 1 up to b of 1 over x squared dx. So when I have an improper integral, what I need to do is to avoid that improperness by replacing that infinity sign, which is not a number, with an actual number, and then allow that number to get as close to infinity as possible. And we do that notationally by a limit as b goes to infinity. Okay, so here's our integral. If I kind of sweep the limit as b goes to infinity under the rug, well, I can solve this integral over here. So if I wanted to solve this integral and I had 1 over x squared, what's the very first thing I would want to do?
Bring it up.
Yeah, rewrite this guy, 1 over x squared, rewrite it as x to the negative 2. So we've got the limit as b goes to infinity of the integral from 1 to b of x to the negative 2 dx. All right, excuse me. So now I'm going to take my antiderivative. And so I've got the limit as b goes to infinity of x to the negative 1 over negative 1, evaluated between 1 and b. Alright, so I might rewrite this and write this as the limit as b goes to infinity of 1 over negative x, which is the same as negative 1 over x, evaluated between 1 and b. And now I'm going to plug in my boundaries. So what I did here is I cleaned up my expression here. So x to the negative 1, I brought my x to the denominator. And the negative sign, the negative 1 in the denominator, doesn't matter if it's in the denominator or the numerator, it's the same value. So now I'm going to plug in my b. So I've got negative 1 over b minus a negative, so that becomes plus 1 over 1. All right. Are there any questions on what I've done so far? Okay. At this point, if I knew what b was, then I would have plugged in the b number, and I'd have my actual value here at the end. But I don't know what b is. In fact, b is going to get closer and closer to infinity. So as b gets really, really big, what happens to 1 over b? Gets itty bitty little, very tiny, and goes to 0. So that term goes to 0. And what happens to 1 over 1 as b gets really big? Yeah, it stays as 1. And so we end up with 0 plus 1, which is 1. All right. I want to pause here for a second. Think about what we just calculated. We just did some math and found out that if we calculate the area under 1 over x squared, starting at x equals 1, and pushing this wall off to infinity, if our units here are maybe square feet, okay? Or, if our units are feet on the x-axis, feet on the y-axis, if I take this area and push b off to infinity, the amount of paint that I need to paint this region right here is enough paint for 1 square foot. Infinite in length, finite in area. So even though you're taking your can of paint that's going to cover 1 square foot of wall space, and you start painting, you're never going to run out of paint, even though you'll never get to the end of your wall.
What?
So as the asymptote, it gets so thin, like for example, because the x-axis is an asymptote there, it never actually touches, and there's area out to, I mean, it's so, it just seems funny that, I trust the calculation, but it just seems funny that because it's asymptotic and that there's a tiny amount of area that just goes and goes and goes and goes.
So what it turns out is that that tiny area gets so small that no matter what number you say, I want to get within 0.000005 square units of 1, I can stop at a point and we'll still be within that value. All right, so this is interesting. So observation is that the limit as x goes to infinity of 1 over x squared is equal to 0. Our function approaches the x-axis. as x gets really big. But the integral from 1 to infinity of 1 over x squared dx, which is the limit as b goes to infinity of the integral from 1 up to b of 1 over x squared dx, is equal to 1. All right, let's look at a second example. The integral of 1 over x dx, starting at 1 and going off to infinity, exactly the same as the last time, but I no longer have a square on my x. My picture looks very similar. F of x is equal to 1 over x. I'm starting at x equals 1. And we are interested in the area under the function f of x equals 1 over x, starting at x equals 1, and going off to infinity. Now, again, this is an improper integral because of that infinity sign. So the very, very, very first thing I'm going to do is to make this integral proper by writing the integral as the integral of 1 up to b of 1 over x dx. And so I'm getting rid of that infinity sign, but I have to pay a price for that. I'm going from 1 up to a big number, but I've got to make sure that that big number eventually heads off to infinity. So step number 1, get rid of my improperness by replacing it with a number, which we'll call b. But the price I pay is that then I need to take a limit as b goes off to infinity. Okay. So here is our integral antiderivative of 1 over x. So I'm going to carry along the limit as b goes to infinity. Antiderivative of 1 over x is natural log of x. We're going to evaluate that between 1 and b. And so we've got the limit as b goes to infinity of the natural log of b minus the natural log of 1. Now the natural log of 1, what is that value? Yeah, that one's 0. And so natural log of 1 is equal to 0. So we can really rewrite this as the limit as b goes to infinity of the natural log of b. All right, any questions so far on what we have? All right, so we've taken care of our antiderivative, we've plugged in the boundaries. We now need to pay our price, which is evaluating the limit as b goes to infinity. Now, the natural log function,
It's just going to keep climbing and climbing.
yeah, it looks something like this. And if I wasn't sure what the natural log function looked like, y equals natural log of x, if I didn't know what that looked like, I would graph it on my calculator. But this function continues to go up and up and up and up and up and up and up. So as b gets really large, natural log of b is also going to get very large. And so the limit as b goes to infinity of natural log of b is infinity.
We need a lot of paint.
We would need a lot of paint for this one. All right, so this integral, on this one, when we observe, the limit as x goes to infinity of 1 over x is equal to 0. Our function, 1 over x, still approaches the x-axis as x gets really large. But in this case, the integral from 1 to infinity of 1 over x dx is equal to infinity. It tells us that the amount of area under y equals 1 over x, starting at x equals 1 and going off to infinity, is an infinite area. So both our ceiling on 1 over x and the ceiling for 1 over x squared, the ceiling approaches the x-axis, but there's something inherently different. the ceiling for the 1 over x is not approaching the x-axis quite as quickly as 1 over x squared. In fact, that's the difference between an infinite amount of area where you're never ever going to be able to paint because you'll never be able to buy enough paint to paint this region, versus integral of 1 over x squared where you need only enough paint for 1 square foot. So that's a little bit strange, and I want to let that sit with you for a little bit, and give you a couple of definitions in here.